So the title of the talk is Introduction to Causal Discovery. And when we talk about causal discovery, typically we're reasoning with and about graphs. And I'll say a little bit more about what that means in this context. So the classic kind of motivating example here is that we've got some treatment variable, call it x, and we want to quantify its effect on some outcome variable, call it y. This could be a policy, maybe a tax policy or something. Could be a website design. For concreteness, let's say x is smoking and y is lung cancer. Does smoking cause lung cancer? Well, graphically, if we think that it does, we might depict this something like this. So we have these nodes that are variables. We have a directed edge linking them. And all this graph says, this very simple graph, is that x causes y. So far, so good. I think that's pretty basic, simple stuff. But we probably have more than just two variables, right? We don't just have a treatment and an outcome. We might have a lot of historical data, as we were just hearing about. So how does that sort of get incorporated into our model? Well, it depends where that data is sort of in a causal structure. If it's a pre-treatment covariate, we might have a graph that looks something like this. So in this case, A is going to be a confounder or a fork variable. For the smoking lung cancer example, this might be like a genetic predisposition both to smoke and get lung cancer. And if that is true, we're going to need to control for that, obviously, in thinking about causal effects. And again, the graphical representation is given here. But it could be that we have other covariates that don't fit neatly in that slot. So for instance, we may have a mediating factor B. Now this actually was what was believed once upon a time in the early 20th century. So Ronald Fisher, who's sort of a foundational figure in the history of statistics, he was a big smoker, and he did not believe that smoking caused lung cancer, and he posited that there's actually a mediating factor. Tar deposits in the lungs was what he said. And smoking does not cause lung cancer, according to him. It causes these tar deposits, and the tar deposits cause lung cancer. Now, if that's true, which it isn't, by the way, but if it were, we might be able to depict it with something like this, where there's no longer a direct edge from x to y, but rather this mediating factor B, and then the edge goes from B to y after that. We may also have downstream effects. For instance, heart disease has been linked both to smoking and lung cancer. Now, C is acting as a collider, we say in this case, because it has two edges coming into it. So we see that this picture has become a little bit more complicated as we've added more and more factors, right? There's different kinds of variables fitting in different places in this graph. So the question, if you remember how we sort of started this whole thing, was, but what's the causal effect of x on y, and how can we use these variables to get it? Well, one proposal, which sounds a little bit like some of what we were just hearing about, would be, we'll just throw it all into a model. If it's a linear model, to make life easy, then we would just get weights, right, for each of these variables, and we would just read off the weight for x after I've controlled for everything else, and that would be a causal effect. Don't do that. That's not right. That's not the correct way to get the causal effect. In this particular graph, we have to adjust for A and only A. This is called the backdoor adjustment formula. I'm now using sort of Pearlian do calculus notation here, so the probability of y given do x, a causal intervention on x, is this conditional probability as we marginalize over A, and only A, because it's a confounder. So, if there's one sort of thing that I hope you can take away from this, it is that we do not just condition on all of the covariates. That will absolutely bias your causal effect estimates, provably. Now, it's a bias. It's not that it's going to make it imprecise. It's not that we're blowing up the variance or something. It'll just be wrong on average. By the same token, we cannot just ignore the covariates. Failing to adjust for the right variables will also bias your causal effect estimates. Causal structure matters. Where those variables are in the graph makes a very big difference. And it's to get a sort of sense for what happens when we fail to adjust for the right causal variables. There's this kind of famous example, you may have seen it, it's called Simpson's paradox. Very weird, very real effect, where a particular relationship between features, in this case x and y, can look one way when you just sort of throw all the data together. It appears that there's this downward slope between x and y. But upon conditioning on the right covariate, in this case a grouping factor, that we see that these are sort of three different clusters, the direction of the association flips. So there's actually a positive association between x and y conditioned on some grouping variable z. This really happens in the real world. So there are cases of medical studies where a treatment appears to be effective for men, effective for women, but not effective overall. There are examples from sports. Someone can have a better batting average than his teammate every year for 3 years, but have a worse batting average over all 3 years. It's very strange, but it's all about what we're conditioning on and not conditioning on when we evaluate these relationships. So again, the causal structure matters. We cannot just have machine learning solve it for us if the model doesn't know where exactly these variables land in a causal order. Okay, some good news and some bad news about everything I've just said. The good news is we've got some pretty good tools for beginning to tackle this problem. There are in fact sound and complete algorithms for computing causal effects from observational data. I have not said anything about experiments, by the way. That's obviously always like another option, but we're assuming in a lot of cases that experiments are either too expensive or complicated or perhaps even unethical to conduct. So we're going to limit ourselves to observational data. This is basically the life work of this man, Yuta Pearl. He's an Alan Turing Award winner. He's a professor emeritus at UCLA, and he is the founder of the do calculus. He, in collaboration with several of his former PhD students who are now sort of big deals in their own right, have pretty much solved this problem. He originally worked on the atomic intervention case. It's now been generalized to other kinds of interventions. We know how to do this when we have the graphical structure. But the problem is, who says we have the graphical structure? Where does that come from? Have we assumed it up front? Have we done some sort of learning process to figure it out? This is the work of causal discovery. So what I mean by causal discovery is a little bit different from causal inference, which is like when we are quantifying a particular effect. The goal in causal discovery is to learn a causal graph, or at least as much about the graph as we can, that corresponds to the true data generating process from a combination of assumptions and observations. We have to make assumptions. There's no assumption-free version of this. And the observations, in this case, will exclude experiments, although there are some methods that would incorporate experimental data, which would obviously be helpful if we could do it. A quick word of caution. Most graphs are unidentifiable from observational data. At least they're not uniquely identifiable. What we can usually get to, though, is a Markov equivalence class. So that's a set of graphs that are possible given the data. Think of this more as like ruling out graphs that are inconsistent with the data. That's what we can do with these causal discovery methods. All right, some more good news, bad news. The good news, there's some really powerful methods. Sound and complete algorithms exist for inferring causal structure under some pretty strong assumptions. Remember I said that there's no assumption-free way to do this. I'm not going to get too deep into what those assumptions are in these cases, but they involve sort of certain assumptions about how your probability distribution behaves. This is a team of researchers at Carnegie Mellon in the philosophy department, weirdly, who basically have, in the 90s and 2000s, kind of solved this problem, at least under, like I said, certain strongish assumptions. So constraint-based causal discovery is what they've sort of really innovated, this group. And when I say constraint-based, I'm contrasting that with score-based and hybrid methods, which I'm not going to say so much about, not because they're not useful, they're actually very useful, but they don't come with the same theoretical guarantees. So constraint-based methods are ones based on conditional independence testing. I'll say a little bit more about what that is in a second. But these methods, developed by Peter Spurz, Clark Leamore, and colleagues at Carnegie Mellon, do come with these soundness and completeness results. The bad news is they rely on conditional independence testing, and conditional independence testing is hard. When I say it's hard, I mean it is like provably hard. If you have continuous conditioning events, it is impossible in general to guarantee that you have power against arbitrary alternatives over and above the level of your test, which is usually like only 5% or 10% in most applications. That's kind of a worst case result. But even in general, we need to make really strong assumptions to do the sort of classic conditional independence testing. And this, I think, is where machine learning can possibly come in and help relax some of those assumptions a bit, generalize our toolkit to expand to new things. So, a quick word on conditional independence. And forgive me, things are about to get a little bit mathy. I'm not going to get too much into the math of it, but kind of just at a high level, conditional independence means that if I already have the information from a variable z, does adding the information from a variable x help me predict y? If not, then we say that they're conditionally independent. If so, then there is a conditional dependence there. This is really important for some classical results in statistics. So the likelihood ratio test is kind of the beginning of all frequentist statistics. There's this really foundational result from Neiman and Pearson called the Neiman-Pearson lemma. which shows that likelihood ratio tests can be used to evaluate conditional independence in a certain class of models. Don't worry about what the math here actually says. I'm just showing it to give you a kind of high-level overview that we've got a likelihood ratio, that's the fraction going on there, so some sort of density for y, with x and without x, that's what the minus, sorry, with the jth x, that's what the minus is showing you. If adding the jth x helps us do better at estimating this likelihood, then we say that it must be important, there must be some conditional dependence present. And we evaluate that with a statistical test on the mean of this variable. Why is this important? Well, there's some really awesome kind of optimality criteria that this test comes with. It is uniformly most powerful, or UMP, if we use the acronym. So it attains the lowest possible type 2 error of any test that controls type 1 error. So if you want to fix your false positive rate, you say, we will not get false positives more than 5% of the time with this test. Well, no test that can do that will ever detect more true positives than this. This is why people like frequentist statistics. It has this optimality criterion. But it relies on likelihoods, which is a really strong assumption. It means we've sort of made some parametric sort of starting points here. We can relax this a bit with machine learning methods. So there's a great paper from a few years back from Larry Wasserman's group at Carnegie Mellon that introduces the leave one covariate out test, or LOCO test. Conceptually really similar to what's going on with likelihood ratios, but now, instead of having a likelihood, we've just got these two different models, the mu x and the mu minus jx. These can be anything you like, neural nets, gradient boosted forest, random forest, whatever you like. And we do a model for y with and without the jth covariate. And then I just compare the residuals for these two. Absolute residuals to be technically right. And the idea is if the model does just about the same when it has the information from the jth covariate as when it doesn't, well, then that jth covariate can't be doing very much. But if it improves a lot, well, then we think it is probably doing something. And again, arbitrary function classes can be used to test this. Another idea sort of along the same lines is called the conditional predictive impact. And the idea here is that we assume access to a set of knockoff variables, which I'm not going to formally define, but basically they share the covariance structure of the input features. And now, instead of having to refit a model for every time we want to do a conditional independence test, we just get the one single model, and we just dunk in the knockoff variable instead. And again, compare the residuals before and after. And the idea is if you don't do any worse when replaced with the knockoff variable, then that variable couldn't have been doing much work. Structurally, though, notice how these are all sort of sharing the same form of like the likelihood ratio test. We have some variable that we're just seeing if its mean is greater or less than 0. One final example, there's a fantastic paper from Rajan Shah and Jonas Peters. This is the one where they sort of prove the hardness result for conditional independence testing, which people had sort of thought was true for a long time, but it's actually really rigorously shown in this paper. And their proposed solution is this thing called the GCM, generalized covariance measure. I'm not going to get into the math of it. Basically, it involves two different models. Again, pick your favorite function class, whatever neural net fancy thing you like, take the product of their residuals, and if that is expectation 0, then we say the null hypothesis cannot be rejected. So all sort of similar like ideas, right? Just sort of cashing it out in slightly different ways. All of these methods behave fairly well in certain types of settings. So this is a big simulation experiment where we compared 4 different function classes, those are your columns, with a linear and a nonlinear data generating process. And basically what you find is that different methods, these are the power curves for these methods as effect size increases, different methods do slightly better in different settings. Think of this as like a sort of no free lunch theorem for conditional independence testing. Nothing is going to uniformly dominate. We know that from theory, but we also see it in practice. If you play around with slightly different data generating processes, slightly different function classes, you're going to get slightly different results. But note how in almost every case, as effect size goes up, we do eventually reach power 1. One notable exception I will point out is that a linear model, that's the far left, fit to nonlinear data is always garbage. That's what we want to see. That's in fact what we see. So misspecification matters. Okay, this is like a lot of stuff, so I'm just going to try and maybe wrap this up with a few sort of takeaway points. If nothing else, the one thing I hope people can take away is that we just can't estimate causal effects without making assumptions about the causal structure. When you put covariates in your model, in your S-learner, T-learner, X-learner, whatever, you are making a causal assumption. You are assuming that that is a confounder. You're assuming that it is a pretreatment covariate. If you are treating it as a mediator or a collider, then you are biasing your causal effect estimates. So causal structure matters. We can't get to just ignore it or assume that the model will solve it for us. Learning graphs is hard. I say DAGs because it's technically a directed acyclic graph, but we'll just say graphs in general. Learning DAGs is hard. If you can encode prior knowledge in any way, I strongly suggest you do so. Now, maybe you have prior knowledge because you know that some features were recorded at an earlier time than another. Well, then we can avoid having to test for the reverse causality, right? We know that that's not what happened. Maybe we have good prior knowledge because it's a scientific field we just know really well. We can make at least certain assumptions up front, and that is always going to speed up the causal discovery procedure and improve its outputs overall. And a final point I'll make is just that I think we can really try to combine like classical concepts, sort of foundational work from the early days of frequentism and Bayesian statistics with machine learning methods. These two can always be fruitfully combined. So the classical stuff usually has really sound theoretical foundations, but relies on some restrictive assumptions. So in the case of the Neiman-Pearson lemma, it's going to be that we have some likelihood model for the data. Machine learning methods, by contrast, are kind of theoretically all over the place in a lot of cases, but they're very flexible. They can take lots of high-dimensional data, for instance, where the classical stuff often breaks down, and they make no or little parametric assumptions on the true data generating process. So bringing these two things together, I think we often get the best of both worlds, and we can definitely do that in conditional independence testing. I'll pause there. Happy to take any questions or comments at this time. Thank you.
Thanks so much. Thanks so much, David. It was a great talk. We have a few questions here. So it's a highly complex field. And we know that in theory, there are kind of strong ideas already, but we know that when we get down to the real world, everything gets a little bit more, let's say, messier. Yeah, and so one of the questions from the audience is, in the context of this, for example, massive industrial data sets, so you have a lot of features with low signal, numerous features, how can a causal discovery methods effectively extract a causal graph that is kind of interpretable for humans, considering the chance of noise, dimensionality of such data sets? What is kind of your tips and tricks for this type of analysis?
Sure. So depends how high dimensional the data is. So one sort of big area for this that you'll often see these methods being applied is like in bioinformatic data sets. So we'll have maybe tens of thousands of genes, and we want to create networks over those genes. This has implications for drug discovery, for drug testing, whatever. It's hard. I'm not going to pretend it's not hard. But often a really useful assumption to make is a sparsity assumption. So you assume that most features aren't doing much work to link to most other features. This is empirically usually true. So like in lots of network analysis of social networks, of biological networks, we often find that sparsity is very common in these things. There seems to be some sort of like natural order to that. Under sparsity assumptions, you can actually get much more efficient results and much sort of cleaner, sparser networks that are also more interpretable. Yeah. And this is, in fact, how a lot of work in like biopharmacology, for instance, has proceeded, is under that assumption.
That's very interesting and very helpful, because in this case also the computation part is obviously very, very hard, and if you use kind of the statistical components even more, but when you relax that, you also lose some of the more the better assumptions that we have. So another question would be, are there any types of variables or other data characteristics that work better with some specific conditional tests? And you discussed several different ways of doing that. From your experience, what would be important to have in mind in that case?
Totally. So, I mean, if the parametric assumptions are true, you'll never do better than the parametric test. So if the data actually is linear, then always use linear models, always get your simple correlation tests and partial correlation tests out. Those are they will dominate any other method, right? So it does matter to sort of look at that. By the same token, as you relax those assumptions and you say, well, I don't want to assume that it's linear. I want to allow for non-monotonic effects or something. It will be harder to detect those. You usually need larger sample sizes. But these more flexible methods can, in the limit, find them. It does just often involve a bigger data set than you started with. If the question is like, what's the best kind of off-the-shelf thing, I would usually say starting with a parametric model just to see how it fits is usually a good idea. So sometimes things are actually kind of neat and linear, and that's great if you can get away with it. And then I would compare the performance of that to a few sort of standard things like tree-based stuff or neural nets and see if you get drastic improvement. If so, well, that's a really good indication that the parametric model is just misspecified.
It's better, yeah. And a final question, a quick one. I think you've touched on some of these things. What is the perfect example of a use case where to apply causal discovery? You discussed some of them.
I mean, there's a bunch. I think the one that's really interesting and important and complicated is the bioinformatic one. So where we do know that some genes are hub genes. We want to target those with our drugs and not the sort of downstream effect genes, which are more like symptoms of what we're actually trying to target. So I'm very interested in those sort of examples, but I think there are other potential ones that could be really interesting. I mean, any case where we've got a lot of data and poor mechanistic understanding is one where these sorts of tools can hopefully help identify at least prune the search space of possible experiments we would need to run, because it can be so astronomical to do the full thing.
Indeed.